Question number 4, here we go. A cylindrical can, open at the top, is to hold 500 cubic centimeters of liquid. Find the height and radius that minimize the amount of material needed to manufacture the can. Verify your answer with either the first or second derivative. All right, picture time. I don't think you really need it, but it helps to look at it. I don't know. You can decide for yourself whether or not it's going to help you. I have a cylindrical can. All right, that's probably one of my worst pictures ever, but we'll go with it. Let's see here. It's open at the top, so the top is all open. They're telling me it holds 500 cubic centimeters of liquid. Well, if it's cubic centimeters of liquid, what does that mean? My units tell me cubic, the volume equals 500 cubic centimeters. But I'm looking for the height and radius that minimize, okay, keep that in mind. I'm looking for a minimum, the material needed to manufacture the can. Well, the material to make the can, what does that represent? Think about that. The material to make the can. That's the outside of the can, that's surface area. So now, they're giving us the formula for volume, and we want to work with surface area. We have to find a way to mesh these two formulas together. There's a reason they're giving us both. If I look at this, to find the surface area of a cylinder, I don't know how many of us remember this formula. It's pi r squared. That's the area of the base, and since it's open, I only have 1 pi r squared, plus 2 pi r h. That's how you find the area around the can. It's circumference, 2 pi r, times height. Sound familiar? Now, there's my surface area, so that's helpful. How do I find the volume of a can? Pi r squared h. That formula you should know. Now, they tell me that the volume is 500. So, how is that going to help me? What are you going to do with these two formulas? Hopefully, you're thinking that you want to get one variable in your formula for surface area so that we can take an easy derivative to find our answer. What I want you to do, hit pause, go to volume, solve for h so that you can sub that in so that surface area only has one variable in it. All right, go ahead and give that a shot. All right, to solve for h, just divide by pi r squared. Now I'm going to take this value and I'm going to sub it in right for h. Surface area is equal to pi r squared plus 2 pi r times 500 over pi r squared. Now, we are trying to take a derivative of surface area. If I want the minimum, that means the derivative has to equal 0 or d and e and have our sign change. Well, I don't want to take a derivative of this. It looks kind of like a mess. So I'm going to try to simplify it. Surface area, pi r squared plus. Looking at this formula, I can cancel out my pi's, awesome. I can cancel out my r, awesome. 2 times 500, 1,000 over r. Well, guess what? I can even make that easier. Surface area, pi r squared plus 1,000 r to the negative 1. Awesome. Taking a derivative of this will be quite easy because it's straightforward power rule. What I want you to do, hit pause, see if you can find your derivative. See if you can set it equal to 0 and solve for the radius because that's what we're going after. Okay. Hopefully you've done this work. This is, you got to be careful. When I subtract 1 from my exponent, I get a negative 2. I want to set that equal to 0. Well, it's going to be a lot easier to set that equal to 0 if I rewrite it as 2 pi r minus 1,000 over r squared. When does this equal 0 or d and e? Well, let's see what happens. Add your fraction over. 2 pi r equals 1,000 over r squared. We can cross multiply. 2 pi r cubed is equal to 1,000. I can divide by 2 pi. R cubed is equal to 1,000 over 2 pi. I can also simplify that. R cubed is equal to 500 over pi, cube root it. Doesn't look too pretty. You do have a calculator. 5.419. Remember, AP Calc rules, everything goes to 3 decimal places. So this is what I've discovered. If the radius is 5.419, I think that will minimize the amount of material needed to manufacture a can. So what I need to do, verify that this actually is a minimum. I know that this will make the derivative equal 0. I need to make sure it's a minimum. Second derivative, easy. Go back to your first derivative formula up here. The derivative of 2 pi r is 2 pi. When I bring my negative 2 down, it becomes plus 2,000 r to the negative 3. Simplify that, 2 pi plus 2,000 over r cubed. Now, what I want to do is sub in what I believe my answer is, 5.419. And if I look at this, look at what's happening. 2 pi, well, that's always positive. And then if I plug this in for my radius, I'm cubing it, it's still going to be positive. So I have a positive number plus a positive number. It's going to end up positive, therefore concave up, therefore I have the minimum. And I always double check this. Is this actually what the question was asking for 5 minutes ago? Yes, I'm trying to minimize the amount of material. Perfect, I got the minimum, that's what I want. Remember, you're being asked to find the radius and the height. So I need to find the radius. I've done that. My units are centimeters on that radius. Now I need to find the height. I have a formula for height from way back in the beginning of the problem. So if I take my answer for the radius, if I take that radius and sub that in up here, then I can find the height. When you sub this in, you know what? You might even want to sub in your original value of the radius before you rounded it. Sub that in up here, and you're going to get an answer, and hopefully what you find out is that the height is the same thing. The height is also 5.419. The height is also measured in centimeters, and those are our final answers. We did it. We minimized the amount of material needed to manufacture the can. Bam.